All right. Hey, girl, hey. So the question you're asking has to do with intermolecular forces. So basically, whenever I have atoms joined together, there's a few different options. So we have chemical bonds, and we can have an ionic, a covalent, or a metallic. Now, how we decide this actually has to do with electronegativity, but in general, ionic is going to come from a metal and non-metal, and I'm sure you know this. Covalent is two nonmetals, and then, surprise, surprise, metallics is two metals. And of course, if we picture the periodic table, well, we find metals here, non-metals here, with the exception of hydrogen, which is over with the metals. All right, so in an ionic bond, well, all that happens is, let's say, for example, table salt, NaCl. All that happens is you have two ions. They become ions by losing or gaining electrons in the valence electron shells. You just have two ions that hang out next to each other. They hang out next to each other because one thing becomes fully positive, another becomes fully negative, and positives and negatives are attracted to each other. That's the basis of chemistry. All of chemistry you can explain because positives and positives are attracted, negatives and negatives are like Elliot and Suzanne. They repel each other. All right, so ionic, pretty straightforward. Metallic, not super relevant here. Covalent is what we're really talking about. So in covalent, spelling's hard. Well, in covalent, I have something like this. Water and oxygen. Oxygen has 2 electrons on the inner shell and 6 valence electrons. Well, all bonding happens to try and get a full outer shell. For the first shell, being full is 2 electrons. For the second shell, being full is 8 electrons. So oxygen, it's not going to gain or lose any electrons. It's going to share with hydrogen. And so what happens here is oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Oxygen, Jacob gets very mad at me when I say oxygen's happy. It's not happy. It just has a full outer shell. Hydrogen has 1, 2. So these electrons count for both. They count for the hydrogen and oxygen to make it full. And so this is how we get something like water. So water, it actually does have this covalent bond holding the oxygen and hydrogen together. And it's made up of, the covalent bond actually has 2 electrons in here. And those electrons are hanging out between the oxygen and hydrogen. Hydrogen has access to them, oxygen has access to them. They kind of belong to both atoms. Okay, so that's interesting. There's a few situations that we can have here. We can have polar covalent or non-polar covalent. So in a polar covalent bond, well, remember I told you just now that these 2 electrons are hanging out between oxygen and hydrogen? Well, think about sharing. If we were to share, let's say, a pizza with your dad, he would probably give us a slice, and then he might take the rest. If you and I were to share a pizza, well, I would give you half, and I would take half for myself. It's the same with atoms sharing electrons. So it could be that the 2 electrons are shared equally. They spend just as much of their time with hydrogen as they do with oxygen. It could also be that electrons are not shared equally. And so in this case, the electrons are not shared equally. Oxygen is greedier. The electrons are going to spend most of their time hanging out with oxygen, less time hanging out with hydrogen. That's because of this property, electronegativity, or how strongly the electrons are pulled towards an atom. So oxygen is more electronegative. It's greedier. It's like your dad eating pizza. And maybe beer would be a better example, I don't know. But the electrons spend way more time with oxygen than hydrogen because oxygen's more electronegative. That's versus something like carbon and hydrogen. They have very similar electronegativities. So they share their electrons. It's just that they share their electrons pretty equally. The electrons hang out about equally with hydrogen and oxygen. Okay, why am I telling you all this? None of this really is IMF yet, but it matters for IMF because it matters for the properties these molecules get. So if I look at polar covalent, well, hydrogen, oxygen, hydrogen, great. Oxygen has the electrons more of the time. It's like the mom in most divorce settlements, right? Oxygen gets the kids most of the time. Oxygen gets the electrons most of the time. Well, what charge does an electron have? An electron's negative, right? So that means oxygen's going to be a little bit negative. Hydrogen's going to be a little bit positive because it hasn't fully given up its electron. It's not like an ionic where we fully lose an electron, but it's almost given it up. It's like the deadbeat dad who takes their kids like once every other Saturday. Like hydrogen has a little bit of access to the electron, but not really. So there are fewer electrons. They're partially positive. Oxygen's partially negative. Beautiful. All right. Now, so what that means is if I have a bunch of waters, well, I'm going to have a bunch of things floating around. Sorry, I did that opposite, with partial negatives, partial positives. And remember, what was the basis of chemistry again? Positives and positives attract, negatives and negatives, or positives and positives, or like Elliot and Suzanne, they repel each other. All right, so anytime I have anything, even if it's only a little bit positive and a little bit negative, it's going to be attracted. When I have these partial positives and partial negatives, that's called a permanent dipole. Partial positives, partial negatives are going to be attracted to each other. Anytime I have partial positive and partial negative, or fully positive, fully negative, they're always going to have some attraction. Attraction between molecules, that is IMF, or intermolecular forces. So one type of IMF is hydrogen bonding. Bonding being the absolute worst name for it because it's not a real bond. A real chemical bond holds together atoms within a molecule. So water is H2O because there's chemical bonds holding together H and O and H. We also have dipole-dipole. These two are really similar. They're basically the same thing. It's just hydrogen bonding is between a partially positive hydrogen atom and a partially negative oxygen, nitrogen, or fluorine. Dipole-dipole is whenever I have a permanent dipole or partial positives and partial negatives, but with any elements. It doesn't have to be this with one of these. We also have the one you asked about, dipole-induced dipole, and London dispersion. So let me actually show you a simulation to help with this. So my slow computer here is just trying its best, and I don't know why it kicked me out. I was logged in. All right, sorry, I'll just chat at you as I log in. I don't really have anything interesting to say, but it'll be a boring video otherwise. All right, let's go. Okay, so cool. So I could have something like this, NH3. Well, this has a permanent dipole, and I have a partially negative nitrogen, partially positive hydrogen. When the partially positive and partially negative just happen to line up and be right next to each other, so something like that, that's an intermolecular force. So you'll see it's not a real bond. It just kind of forms and unforms, forms and unforms. This is what we would call a dipole-dipole because I have a permanent dipole. Now, if I have that partially positive and partially negative thing with a non-polar molecule, notice with, yeah, that's not helpful yet. Notice with methane here, CH4, everyone's sharing equally. It's like a custody arrangement where the kids go 50-50. Carbon and hydrogen get those electrons exactly the same, not exactly, but almost the same amount of time, so there's no partial positives, partial negatives. However, when I'm in a situation like right now, where the CH4 gets close to a partially negative thing, well, what do negatives and positives do? They attract. What do negatives and negatives do? They repel. So when my partial negative is near CH4, it's going to repel any other negative things, repel any other electrons. So if you think about that CH bond, all right, iPad, you can do it. Well, of course. Okay. So if you think about that CH bond in CH4, well, the electrons are just hanging out between C and H, but they're moving around totally randomly between C and H. When CH4 gets close to NH3, NH3 has a permanent dipole, another way to say that, partially positives and partially negatives because of the type of covalent bond it has. Well, I drew this really shittily, huh? Let me fix it. Let's get this close by. Well, okay. So now I have negative things near my H. Whatever negative things, electrons specifically, are near H, when it's next to another negative, these are going to be a little bit repelled. That's going to make, just for not even a second, like a teeny portion of a second, it's going to make that H partially positive. That's a dipole-induced dipole. And then we also have London dispersion. London dispersion happens, let's get rid of this, so that's dipole-induced dipole. London dispersion happens when I have just a totally nonpolar molecule. And just remember, those electrons are always randomly moving around. So just by random chance, every split second, you'll have electrons more on one side than on the other. And so electrons totally randomly moving around. And so you can get into a situation where two molecules next to each other randomly happen just really, really briefly to have a partial negative and partial positive right next to each other. And that's what we call London dispersion. So these are all a spectrum of intermolecular forces. None of them are bonds. It's just how molecules stick together. So if I have a glass of water, for example, well, within that glass, I have a bunch of waters. I know those waters are all sticking together, though, because, well, they don't just float away. They all stick together in my water glass. And so the thing that sticks them, the thing that holds them together, is intermolecular forces. And within those types of intermolecular forces is the one that you asked about. Of course, when we break those intermolecular forces, the water molecules are no longer held there. That's what we do when we boil or evaporate, when we have a gas. All right, Chica, I hope that helped. I love you so much, and talk soon.